Hello, my name is Ángel Cardama. I'm a professor at the Universitat Politécnica de Catalunya, and today we're going to talk about wireless communications. The term wireless comes from the old times, although we have now begun to use this name quite frequently related to mobile communications. This is just a contraposition to the word wired systems, which were the first to develop during the early 19th century. When telegraph lines had to be deployed, they used two wires for the sending the messages across from one point to another, and that same type of lines were used by the telephone and also later on the power lines for the electrical system. When Marconi started to test his telegraph system, then he really coined the term wireless when he communicated by radio waves from one side of the Atlantic coast to the American side. And then radio came along, and we had a mixture of wired and wireless systems. Wireless systems employ antennas, and wireless systems just cables to go from one point to another. Wireless systems are good in the sense that they can reach very far away with just an incremental decrease in the signal, while wireless systems are really good in short distance because you keep adding losses as you increase the distance. But today we have a mixture of both. At home maybe we can reach our access point to the internet by a Wi-Fi or the phone with a cordless. In other cases, we just communicate with optical fibers to the central station. We really have a mixture of things. And in some cases, there's only one way to do it, and it's wireless. For instance, this is the case when we want to communicate with a mobile or just using a satellite. Today we're going to concentrate in those systems. So let me show you just a simple image of what is involved. Here you have the technical aspects that are most relevant. It's just the set of antennas and cables and links to bring the signal. On the left, this is the communication tower in the city of Barcelona, and the upper stages, the ones that are here, are just the broadcasting antennas. They are broadcasting all FM and TV signals on the metropolitan area. And on the decks below, you can see plenty of antennas. Most of them are radio links, are parabolas that you can see. Maybe this one is clear to see, and on those stages. But there are a large number of antennas around for mobile communications, for dispatching, police, firefighters, all kinds of services you can imagine. On the center part, this is just an old mobile phone tower. And I think it's interesting because here you can see all types of antennas. Some are covered by radomes. In some of the cases you can see those are just whip antennas. So there are very different structures in there. And this is the radio link antenna because those base station antennas will just send the signal to another point by means of this link. And the third one is just a Wi-Fi antenna on the campus of the Universitat Politécnica de Catalunya. This is a very small antenna, it's about 20 centimeters long at most, and this is just a cable, it's a simple one. This is just the brick size, to give you an idea. And this is just an antenna that you can see around in many, many places. All those systems have in common the use of antennas, and to send the signal from this antenna to the other one, we have to establish a set of parameters that will bring you the basic data on the communication channel. And this is what we are going to see today. This is the outline for the session. We will start talking about parameters, basically the antenna parameters that are relevant to our talk. Then we cover how those antennas directionally send the signals in different directions of the space. We will establish a power budget, how much power I put in the transmitting side and what I get on the receiving side. Signal to noise ratio, which is the basic parameter to define the quality of the link. And we briefly talk about modulations and figures of merits. So this is going to be the outline for today. Let's start with the parameters. The most important parameter related to the circuits that are connected to the antenna, the transmitter, is the impedance, the antenna impedance. And the first thing we have to describe is the antenna. The antenna is just, normally is a metallic body that really has one single mission, is to accept power from the transmitter and send it to the space. And on reception, it does the opposite. It extracts power from the wave that is coming towards and sends it to the receiver. When you look at the port, the antenna has a connector and entry port. There, the main parameter is the impedance, and it's listed here. This is just the impedance. And it's just the ratio of the voltage to the current on the port. It has a real and an imaginary part. It has a resistance and a reactance. We call this R and X. I will put here just an A to identify this as an antenna impedance. And it's dependent on the frequency. It changes with frequency. If there's no reactance at a certain frequency, then we say that the antenna is resonant. This is an important parameter because in most of the cases, the antennas are going to be connected to cables. And cables have a standard impedance of 50 ohms, except in one case, which is the TV cables, that they have a 75 ohms impedance. But for most practical purposes, we can think that we only want to have 50 ohms resistance or impedance in the antenna. That means that we have to work with antennas that are resonant at the frequencies we want to transmit. The resistance has two components. One is clear, is the loss resistance. If the antenna has losses, then we have to take this into account. But the other one is the most important. It's what we call radiation resistance. And this is not a resistance in the sense that is associated with losses. It's just something that tells you that there's current coming to the antenna, and this antenna is going to send waves to the space. It's going to send power. So there's a transfer of power from the antenna to the space. And this transfer of power appears as a resistance. And we call this the radiation resistance. Okay? So it's there as long as the antenna is radiating. The loss resistance is normally due to metallic losses, to the losses on the metals, which are really not relevant if the frequency increases. Except for one case, which we use very frequently, is on the AM radios. The antenna is a coil that is loaded with the ferrite. It's a very small antenna, but there you have losses associated with not only the metallic parts, but also the magnetic behavior of the ferrite rod. Then, once we have considered those resistance, we just add them, and this gives us the total resistance of the antenna. Then we have to distinguish power, and we have to define some terms here. The first term is the total power radiated by the antenna, and this is just, since we are talking about radiation, is the square of the current that is entering the antenna, the input port of the antenna, squared times the radiation resistance. But the net power that is being accepted by the antenna from the transmitter is the sum of those two terms. The radiated, the one that we are sending to space, plus the power that we are losing on the antenna, is the dissipated power. And they both add, and we call this the accepted power. This is the power that is being taken from the transmitter by the antenna. And this accepted power is just the square of the current times the resistance. And here we have the sum of two terms. Here I have written this in this way, the square of the current times the resistance. Sometimes, when talking about power, you will be seeing here a term 1/2. Be careful with this, because that depends on how you define the current. The convention we are using in this session, in this lecture, is that this current is the root mean square, the RMS, or sometimes we call the effective value. This is not the peak value of the current. If you use the peak value, then we have to put here 1/2. But if you use only the effective value, then this is the right way to say it. So this is the accepted power. And now we can define an efficiency of the antenna as the ratio of the power we radiate to the power that is being accepted by the antenna. And you see that clearly this is just the ratio of the radiation resistance to the input resistance, which is the sum of the radiation and the losses. If there are no losses, the efficiency is going to be 100%. If the losses increases, then this term becomes lower than 1. You can give it as a number or as a percentage. That's the parameter you see. We normally want to have this value as close to 1 as possible, and for most purposes that's the case. If not, you have to take this into account. Now let's talk briefly about the link. In a communication system, we have the antenna, the transmitting antenna, and the connected transmitter. And we have on the receiver side the similar situation. And both antennas are separated distance r. If you look at the transmitting end, here we have connected directly the transmitter to the antenna. In most of the cases, you have cables and some other things in there, but let's stick to the simplest case, transmitter and antenna. From the circuital point of view, here we have just the transmitter represented as a voltage generator and the impedance of this generator, this voltage generator. And we call this G, voltage and impedance. And on the antenna port, we have the side of the antenna, which is just a linear passive device, it's just an impedance, and we have voltage and current. So this is just a simple loop, generator and antenna, transmitting antenna. The maximum transfer of power happens when we have matched conditions. And matched conditions means that the antenna impedance and the transmitter impedance are complex conjugates. That means that they have the same real part and the imaginary part is just one, the negative of the other. Under those conditions, we have maximum acceptance of power, and this will be related to the square of the voltage divided by 4 times the voltage generator resistance. If you don't fulfill this condition, then we say that we have a mismatch. That means that we are not accepting all the power that could be possible. And when this happens, then we define a mismatch coefficient that will give us the ratio of the accepted and the maximum power we could accept. And this is also related to the reflection coefficient. In which sense? If we could deliver the maximum amount of power to this antenna and there is a mismatch, that means that part of the power incident on the antenna will be reflected, will be returned to the generator, to the transmitter. And this is why we have here, this is 1 minus the square of the reflection coefficient. And this could be related to the impedances of the antenna and the generator. And here you have the resistance and the reactance. And you will see that you could maximize this term when those two are one equal to the other negative, this term will cancel, and those two terms are equal, and this is what you get in there. So this is one parameter you should take into consideration. If things are matched, you are doing the right thing, the correct thing. If there's a mismatch, you have to take this into account. Now if we move to the receiving end, then here things change. There's a wave that is arriving to the antenna, and power is being transferred to the receiver. Now the antenna behaves once again as an active element, as a voltage and impedance, and we have the receiver here represented as a load. Here the terms are similar to the previous one, and we define the available power as the maximum power transfer. And once again, is the square of the open circuit voltage divided by 4 times the antenna resistance. And if there's a mismatch, then we have a reflection coefficient which is the same we saw before. So this is just the right way to go, and those are the main parameters we have to deal with from the point of view of impedance.